All right, welcome to 5.5 and Math 31, which is the entire curve sketching process itself, which um, looks intimidating for sure. Usually when we test this, we actually give you the headings or the title of the headings so that you don't have to remember all that, because it is a lot of stuff to remember. Just, talking through them quickly. Domain, you're pretty used to. Intercepts, you've been for a long time. Symmetry is new this year. Just keep in mind when we check for odd versus even symmetry, if we know it's even symmetry, then if we have to the left of the y-axis, then we really have to the right of the y-axis as well. Odd symmetry is a little bit harder. Typically, knowing that it has odd symmetry isn't all that useful when you graph it, except for maybe looking at it after to evaluate that. Asymptotes, a lot of students will forget to do both the vertical and the horizontals. We need to consider both. Then we have intervals of increase, decrease. That leads to our local mins and max. And then concavity, and then finally we sketch the curve itself. All of this is a lot at once, for sure. And part of the reason why we do headings like this is so we can break it apart a little bit piece by piece, and basically be able to deal with it just a little bit simpler, I think, which is a pretty big advantage. So what we're going to do is we're going to do it with a relatively complex function. This is, a rational equation, not the easiest. This process is certainly simpler with simpler functions, as you might expect. All right, so heading A, which is domain. Right away in domain, at least in high school, there's not too many cases that we have to run into. We can't divide by 0. We can't take the even index radical of a negative. You can't take the logarithm of a non-positive number. Those are the main ones. For this particular question, the restriction on the domain is that the denominator, 1 minus x squared, cannot be equal to 0. Well, when we factor that, we get 1 minus x times 1 plus x can't be equal to 0, and I get that x cannot be equal to positive or negative 1. Now, these are really important because they do become where we examine the vertical asymptotes for this function at. So we're going to keep that in mind. B, and I'm going to kind of, hopefully not take too much space. Sometimes students do struggle with getting this on one page, and typically when we do assign questions like this, there isn't a lot of them because it does eat up a lot of space. Like this certainly fills up an entire page in my notes, at least. All right, for our intercepts, we're looking at x-intercepts and y-intercepts. I actually always like doing the y-intercept first because it's simpler, I think. It's when x is equal to 0. Well, when x is equal to 0, and I'll put that's f of 0, I would have 0 squared over 1 minus 0 squared, so that would be 0. So this graph passes through the origin at 0, 0. I should consider x-intercepts as well. There may be another one. In this case, there isn't. So I'm going to put that both x slash y intercepts, I'll try to spell that right, are at the origin, so 0, 0. So this graph does go through the origin. All right, the next one we have to check, that's heading C, is symmetry. So the way that we're going to do that is I will check f of negative x, f of negative x, and we get that is negative x squared over 1 minus negative x squared, and that gets me to x squared over 1 minus x squared, which means that f of negative x is equal to f of x, so we have even symmetry. And that's useful because we do know that it's going to be symmetrical about the y-axis, much like, if you drew a vertical line through a human being, we would be symmetrical through that vertical line or over that vertical line as well. All right, next up we have the asymptotes. And it is very important that you consider both the horizontal and the vertical. I'm going to do vertical first, so we're going to look at the limit as x approaches 1 from the positive, the limit as x approaches 1 from the negative, and then we're also going to do the limit as x approaches negative 1 from the positive, and the limit as x approaches negative 1 from the negative. Now we're doing all these limits on the same function, x squared divided by 1 minus x squared. One of the nice things about this particular function is that the numerator is always positive. X squared is never negative. You can't say the same thing about 1 minus x squared, but certainly is true for the numerator. So all we really have to determine is whether our denominator is going to be a very, very small negative number or a small positive number. So as we take that limit as x approaches 1 from the positive, so like 1.1, what we're going to have is a positive divided by a small negative. So this is going to go to negative infinity. All right, now try to go, if you're struggling with that, go back to the lesson we did on asymptotes and make sure you understand exactly what I'm doing here. I am looking at the behavior of the function as it approaches its non-permissible values. As we approach 1 from the negative, so like, 0.9, we would still have a positive number, but now we're going to divide it by a very, very small positive value. 1 minus 0.9 squared ends up being I think 0.19, which is positive. So this is going to go to positive infinity. Now you don't need to do this, but I like the idea then of if we know my vertical asymptote is here, not looking at anything else in the function, I know that it veers down. Oops, I did that the wrong way. It veers down to the right of it and it veers up to the left of it. That's really all we did there. And that's going to be useful when we draw the graph itself. Looking at this, I'm going to cheat a little bit. I'm pretty confident you can do this. And it has even symmetry. So recognizing that even symmetry means that as I approach -1 from the right, it's actually going to go to positive infinity. And as I approach -1 from the left, it's going to go to negative infinity. You can use the exact same concept we used on the left-hand side there, those left-hand limits, I suppose, and you would get the same technique. All right, the other one we need to consider is the limit. In this case, it actually doesn't matter. So I'm going to look at the limit as x approaches positive and negative infinity of x squared over 1 minus x squared. The reason I say it doesn't matter is my variable is squared everywhere in the function. So if I were to put in negative infinity in for x, it would behave just the same as if I were to put positive infinity in for x because it's squared. So what this is going to be equal to, the way we're going to deal with this is I'm going to multiply the numerator and the denominator by 1 over x squared. And this becomes the limit as x approaches positive and negative infinity of 1 divided by 1 over x squared minus 1. Now, to deal with this limit, anywhere we have a constant divided by the variable is 0. So this limit is equal to 1 over -1. So we get -1. Now, I always like kind of summarizing just a little bit about this. We have vertical asymptotes when x is equal to positive or -1. And we have a horizontal asymptote when y is equal to -1. And that's that heading. All right, those are, I don't know if I'd call them the easier ones, but they are typically the ones that students kind of excel at because usually you've done them before or at least looked at something similar to them before. Really where chapter 5 gets tricky is intervals of increase, decrease, local mins and max, and then concavity as well. But if you take it piece by piece, you have done all of this before. We just haven't done it all together. All right, so in E, we're going to look at the increasing and decreasing intervals. So the way that I'm going to do that, I'm going to put it here again so we can make the connection. F of x is x squared over 1 minus x squared, which means that f prime of x is 2x times 1 minus x squared minus x squared times -2x, all divided by 1 minus x squared squared. Now, that is some pretty classic quotient rule. You have to practice that. You have to keep chipping away at it because we have to get pretty comfortable with that. We also have to be able to simplify it. So f prime of x, I'm going to distribute that first. I get 2x minus 2x cubed plus 2x cubed, all divided by 1 minus x squared squared. And then when I clean that up as much as possible, the 2x cubed terms are going to cancel. So I get f prime of x is 2x over 1 minus x squared squared. So my critical numbers are what makes the numerator equal to 0, that's 0, and what makes my denominator equal to 0, because that would result in f prime being undefined. So we're also going to have positive and -1. Now, really importantly, we know that positive and -1 are not in the domain of the function. That does not mean that it can't change from increasing to decreasing. In fact, you'll see in this question, I believe that it does. You can't get too caught up in thinking that, I'm only looking when f prime is 0. You also have to consider when it's undefined. So from those numbers, we're going to set up our sign chart. So we have -1, 0, +1, which makes the intervals 1 to infinity, 0 to 1, -1 to 0, and -infinity to -1. I'm going to take my factors, which are 2x and 1 minus x squared squared. And then using those, we're going to evaluate if f prime of x is positive or negative. So I'll drop these verticals down. Nice thing about this is 1 minus x squared squared is always positive. Whatever 1 minus x squared is, whether it's 0, negative, or positive, it gets squared after. So that will be a positive at all or in all of these intervals. 2x, a little more complex. 2x is positive when x is positive, negative when x is negative. So it's negative in my first two intervals and positive in my last intervals, which means that f prime of x is negative or decreasing, still negative or still decreasing. Then it switches to increasing, so it's positive, and it's increasing at those points. Now, again, nice to summarize at least a little bit about this, is that we are going to identify then that f of x is increasing. And this is really important. You have to put the interval as 0 to 1 and 1 to infinity. Now, I'm going to put or there because and has a pretty specific meaning when it comes to, the real way that we do this mathematically is we put this capital U, which means union, or and union basically mean the same thing. You cannot just put 0 to infinity because the function is neither increasing nor decreasing when x is equal to 1. The function doesn't exist. So we can't include that in our increasing intervals. And I know a lot of students get frustrated by that, but it is really important that when the function is undefined, it doesn't exist, much less increasing or decreasing. So this function is decreasing when x exists from negative infinity to negative 1, unioned with negative 1 to 0. Again, if you're putting or instead of union, you are totally okay with that, or you are okay doing that. That's definitely a little bit of set notation that we don't get too much until later on. Now, local maxes and mins are part of this as well. We could do our first derivative test. And what our first derivative test is showing me is that because the function is switching from decreasing to increasing, and I'm going to write this out because it is a little bit of a doozy. I'm going to say that f prime of x is less than 0 when x is less than, I guess that's 0. That's kind of weird. And we can also say that f prime of x is greater than 0 when x is greater than 0. Now, our first derivative test, I really spelled that bad. First derivative, there we go, test, because it is switching from decreasing to increasing, we know that at x equals 0, f of x has a local min. Now, it may be absolute. We're going to wait until we look at the full graph to talk about that. In this case, it's not absolute. It's local. But it's important that that local min, when x is equal to 0, it's the point 0, 0. Right? That is the local minimum on our curve. All right. One heading left, which is concavity and points of inflection. What we're going to need for this last heading, I'm going to kind of switch colors here again. I've been putting the letters kind of haphazardly here. It is G. I forgot to label this as F. F is about the local mins. So in G, which is concavity, and I'm just going to put /IP, which is inflection point, we are going to need our first derivative. Well, f prime of x, in at least its simplified form, was 2x over 1 minus x squared squared. And some of you might be thinking, man, this is gonna suck. That's a relatively complex first derivative. The second derivative is just going to be more complex. And you're not wrong. That is certainly a challenge in these questions. And it's one of those things that when you're working through these questions, you do need to at least put a little bit of faith in your kind of abilities. But unfortunately, it does mean that if you mess up the first derivative, the second derivative typically goes south as well. So please do make sure that you're using some of those little kind of checks and, maybe putting it into your calculator, checking f prime as well. That's a really useful way of doing this. If you do have access to a computer in Desmos, you can type in f of x is equal to such and such, and then put on the second line y equals f prime of x. And then you can actually judge whether that graph is realistic or not. All right, so what we need to do is take the second derivative. And it is certainly a little bit complex. Again, what I like to do is I like to take the existing denominator. I didn't do it above, but I usually do. And I'm going to take that existing denominator of 1 minus x squared squared, and I'm going to square it. And you do start to get kind of nested exponents when you do this, but we'll simplify that in a minute here. The numerator is going to be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. And this is where it gets tricky. The derivative of 1 minus x squared squared is 2 times 1 minus x squared now to the power of 1 multiplied by the derivative of the inner function, which is negative 2x. you need to make sure that you've practiced, all those wonderful chain rule and quotient rule questions. They weren't there to torture you. They were there because we knew that this type of second derivative was coming. All right, so looking at my numerator, I am going to factor out a 2 and a 1 minus x squared. Now what that leaves me with, and I'm going to use the square bracket here, is 2 times 1 minus x squared divided by 2 times 1 minus x squared is 1 minus x squared. I'm going to leave it in a bracket. Then I'm going to subtract. I'm going to factor the 2 out, so that's left as x. The 1 minus x squared actually gets canceled, so I have a 2 and a negative 2x left in that second term, and I'm just putting a squiggly line underneath there as well. The squiggly line should actually go all the way there. Now, you certainly could have just taken out the 2 times 1 minus x squared, because that's what we factored out of, but I like to do that piece by piece just to practice my factoring. And now we know that my denominator is 1 minus x squared to the power of 4, because squared means to the power of 4. We're going to simplify this further, and there's a lot of simplification in this. We're going to say that f double prime of x, then the 1 minus x squared will cancel with 1 on the bottom. So I'm going to put a big fraction here. That 2 is still in front of that square bracket. And now my denominator is 1 minus x squared cubed, which is a pretty important difference. Now I like doing this because it can get a little bit confusing seeing all this at once. That square bracket is 1 minus x squared plus 4x squared. So when I simplify that in my square bracket on this step, I am going to write that as 1 plus 3x squared in a square bracket. And I really did kind of maybe overjudge how much space I was going to need for that, but it's not going to move very friendlily. So I'm just going to kind of move that. I'll rewrite it. It looks too weird for me to handle. So this would be 1 minus x squared cubed. All right, a lot of work there for sure. What we need to do now is deal with that derivative as is. And I think I might have made a mistake. I'm just going to pause this for a second and check my work, because if our second derivative is wrong, then we're in trouble and everything looks okay. So we're going to roll with it, and I hope I did it correctly. So what we're going to do at this point is we are going to find out when f double prime at x is equal to 0 or undefined. And there's two ways that can happen. If the numerator, so 1 plus 3x squared, is equal to 0. Well, this would be x squared is equal to negative 1/3. That has no solution. So there is no point where f double prime is equal to 0, but f double prime could be undefined. It's undefined when 1 minus x squared, technically cubed, is equal to 0. This happens when 1 minus x squared is equal to 0, which is x is equal to positive or negative 1. Now, there is something that we can do kind of right away. X equals positive and negative 1 are our only potential inflection points. What's f of 1, though? What's f of negative 1? Undefined. So I want to write underneath this, because our function, and I'm actually going to put at positive and negative 1, is undefined, there are no inflection points. And that's something that can be a little frustrating for students. I'm not saying that this graph is always concave up or always concave down. I'm just saying that there isn't a point on the curve where it switches from concave up to concave down. Now, really what's going to happen here is the concavity switch is actually going to occur over the asymptotes. And we'll see that when we make our chart. I got to make sure I get everything that I need for the chart. So I'm going to put that, big number line there. I'm going to put negative 1 here, positive 1 here. This interval is negative 1 to positive 1. 1 to infinity, and negative infinity to negative 1. I'm going to drop these lines down, and then for my factors, I am going to put, and this is going to look a little weird, but 2 times 1 plus 3x to the power of 2 can actually be written together, because 2 is always positive, and 1 plus 3x squared is always positive. So that is positive on the domain of the real numbers for x. 1 minus x squared cubed, though, is a little bit different. So 1 minus x squared cubed, and then we're going to look at what f double prime of x is doing, just if it's positive or negative. 1 minus x squared cubed is positive when 1 minus x squared is positive, and it's negative when 1 minus x squared is negative. Because 1 minus x squared is cubed, we're going to see that same sign show up. So from negative infinity to negative 1, let's pick negative 10. 1 minus negative 10 squared is 1 minus 100. That is definitely negative. from -1 to +1. So let's say when x is equal to 0, it's positive, and from 1 to infinity, because this has even symmetry, I know that it is going to be negative there as well. So my second derivative is negative and concave down from -infinity to -1. It's positive and concave up from -1 to +1, and it is negative and concave down from 1 to infinity. Now that's, again, something that's important to summarize. So I'm going to put that it's concave up, shorten that a little bit, and concave, oh, I spelled it wrong, down. It is concave up when x exists from -1 to 1, and it's concave down when x exists from -infinity to -1, unioned with 1 to positive infinity. All right, lots of stuff in these questions. I fully appreciate that, but you have to make sure that each of these individual pieces are things that we've done before. Putting it all together can be a little bit tricky. Now, hopefully you've managed to put this on, one page or maybe a couple pages that you can look at the same time, because what I'm going to do now is I'm going to make a sketch of the function. And this is technically h, which is our graph. I always recommend that we know several points. You should put those on there first. Well, okay, I say several points. We know 1 point. We know that it goes to the origin. And I'm just going to put that 0, 0 is right there. The other, I guess, attributes of the graph that we know are the asymptotes. We know that we have a vertical asymptote right here when x is equal to 1. I know that I have another vertical asymptote over here when x is equal to -1. And we know that we have a horizontal asymptote when y is equal to -1. Those are all headings that we did already. What we need to determine, and this is really important, that my function from -infinity to -1 is both concave down and decreasing. There is only one way to draw that. Concave down and decreasing with those asymptotes looks like this. And I do want to draw this as well and talk about why it is not what I've drawn in green. The reason that it can't be what I've drawn in green is kind of twofold. One, well, threefold. This is increasing. If we talked about the slopes of that green graph, it's going up. It's concave up as well because the slopes are increasing. And then really importantly, there's an x-intercept there. My function only has one x-intercept, so it cannot be that green section. So I'm just going to get rid of that. Now, here's the beauty of even symmetry. If the far left from -infinity to -1 looks like that, then the far right needs to be a reflection across the y-axis. I didn't draw that very well, but we do see that this is symmetrical about the y-axis. So the y-axis should give us that mirror line so we can look at either side. Now, between -1 and +1, the graph is concave up. It's decreasing from -1 to 0. So that means that it has to look like this. That's decreasing and concave up. On the right-hand side of 0, so from 0 to 1, the function is increasing and it's concave up. And so this is a pretty reasonable look at what this graph looks like. And then just to really get the full meal deal, 0, 0 is also a local minimum. Now, this graph does not have an absolute min or an absolute max because it goes to positive infinity and negative infinity. One of the things that wasn't addressed in the question, and it didn't really need to be, I like talking about domain and range. So x can't be equal to positive or -1, and it's any real number other than that. Y is a little trickier because y is greater than or equal to 0, and y is less than -1, and any real number within those intervals. It's like the function misses this gap of information right here. But what makes this harder, I think, is that 0 is valid, but then when we get down to this y value -1, it approaches that but never actually touches it. And that does make it a trickier interval to talk about. If we wanted that in interval notation, I would say that y exists with a round bracket on the lower bound, -1, and a square bracket on the upper bound at 0. That's not something that we commonly run into, but certainly with more complex functions, that can definitely happen. All right, we are not doing 5.6, so this is the end of chapter 5 for the digital kind of instruction here. Make sure you're trying those questions. I know it's a lot per question. That's why there's only 5 of them. The more complex the function, the harder this is. Please make sure you are exploiting the fact that you have, technology available to you, because that is a really good way of kind of confirming the calculus that you're doing within the problem. And as always, email me if you're having issues. I will make a separate video talking about something in more detail and try to help you as much as I can.